Here we go. So, today we're going to continue using some U-Substitution. We're going to use U-Substitution to kind of round out our missing trig integrals that we have not quite figured out, okay? So, before we do that though, I'll kind of read this little blurb right here. So as we continue our study of integration, we will devote much time to integration techniques, right? Already kind of have done that, right? U-Substitution is one of those major techniques for integration. All right. To master these techniques, you must recognize the form-fitting nature of integration, okay? Right? Getting things into the right form that we use, okay? So in other words, for example here, right, your temptation might be, when you see something like 1 over u to the 1/2, your temptation might be, natural log. It's 1 over something, okay? But no, right, the integral of 1 over u by itself, u to the 1 here, right, that gives us the natural log of the absolute value of u plus c. This, right, the form this is going to fit into is we rewrite it as u to the negative 1/2 du, and then we integrate that using the power rule, right? We add 1 to the exponents, becomes u to the 1/2 over 1/2 plus c, okay? These subtle differences, right? They look so similar, but the results are so different, right? 1 over u to the 1, natural log of the absolute value of u. U to the negative 1/2, or 1 over u to the 1/2, right? That's the power rule there. Okay, so we want to be really careful about making sure that these things fit exactly, with our integral rules and stuff like that. Okay? So, guidelines for integration. Number 1, memorize a basic list of integration formulas. By the end of section 5.8, right now we're going to be finishing up 5.7 today. 5.8 is inverse trig. You will have 20 rules. You will have 20 rules by the end of section 5.8. Number 2, so once you have that list of basic integration formulas, number 2, find an integration formula that resembles all or part of the integrand, and kind of by trial and error, find a choice of u that will make the integrand conform to the formula, right? So it's about choosing your u wisely, okay? You are going to choose poorly sometimes. That's okay, all right? You then need to be able to diagnose, I did not choose correctly here, I need to try something else. All right? And then finally, number 3, if you cannot find a U-substitution that works, try altering the integrand. So like manipulating, the integrand itself. Some options for that, you might try a trigonometric identity. You might try multiplying and dividing by the same quantity, or adding and subtracting, like an opposite quantities, I guess I'll say. Be creative, but patient most of all, okay? You must, persevere through some of these problems. All right? And of course, if you get super frustrated, you can, of course, we can look at it and help figure it out. Except for it's a test, then you're on your own. All right? So, Marlo, do you have a question or a comment?
No, we're good.
You're good? Okay. Good. So, let's take a look at tangent of x dx. Okay? Do we know how to integrate tangent of x dx? No, okay? We know how to integrate secant squared of x dx. Bless you. What is the integral of secant squared? Tangent. So we can integrate something to get tangent, right? We can take the derivative of tangent to get something. But integrating tangent, a little bit funky here. But we know tangent is equal to what ratio of trig functions? Sine x over cosine x dx. In this equivalent format, what technique can we use to help integrate this? U-substitution. We're going to let u equal what in this case? So, right, we could, if we look here, right, I could let u be sine of x. I could let u be sine of x. The derivative of sine, du, would be cosine. But I need to have 1 over cosine here, right? It's not just cosine that I have 1 over cosine, so it wouldn't be quite right. Instead, we're going to choose cosine here, which is in the denominator. Okay, the derivative of cosine is negative sine x, and I'll put the dx there too. Okay, we have a positive sign, so I'll move the negative over here, make it, bless you, negative du equals sine x dx. Okay, and so we have then negative integral 1 over u du. And what is the integral of 1 over u? Natural log of the absolute value of u plus c. So therefore, natural log of the absolute value of cosine of x plus c.
I like this. This is nice.
Okay?
This is a lot better.
Okay. So you can see how we derive the integral of tangent, right? Or how we come up with the integral of tangent, right? So if you have trouble with memorizing it, if you can remember how we get the integral of tangent, then you can kind of like do that quick work on your tests, if you need to. If you happen to forget what the integral of tangent actually is, if you don't memorize it, you can kind of figure it out, okay? So turn the page here. Alrighty. And now we're going to have all 6 trig functions, integrals, along with some of the derivatives of some of the trig functions. Well, yeah, we'll also be able to integrate some other like specific kinds of combinations of trig functions as well here too, right? So we just got done doing the tangent, so let's go ahead and just rewrite that one, right? It's negative natural log of the absolute value of cosine of x plus c, or I should put cosine u, my bad, because we're using u here, cosine u. Okay? Anyone want to take a guess here? What will the integral of cotangent of u du be? So it'll be natural log, no negative in this case, natural log of the absolute value of sine of u plus c. Okay? Cotangent integral is done very similarly to tangent. Remember, cotangent is cosine over sine, so you let u equal sine, and then your du is cosine, and then so on and so forth. There won't be a negative in that one. Okay? We already should know the integral of sine. What is the integral of sine? Negative cosine u plus c. Okay. We already know the integral of cosine. It is positive sine u plus c. Okay. We already know the integral of secant squared. What was that one? Tangent of u plus c. Integral of cosecant squared, therefore, will be negative cotangent u plus c. Okay. Integral of secant u times tangent u du. Secant u positive, secant u plus c. Okay. And integral of cosecant u, cotangent u, negative cosecant u plus c. Okay. And so then it's just secant and cosecant, whose integrals we don't know still. We're not going to derive these ones. I'll just give them to you here. Okay. The integral of secant is the natural log of the absolute value of secant of u plus tangent of u plus c. And then for cosecant, it will be the negative natural log of the absolute value of cosecant of u plus cotangent of u plus c. Okay. So if you, I agree, but I will say this, right? We know the derivative of secant is what? That's what it's equal to is 1 over cosine. What's the derivative of secant, though? Secant u tangent u. And then its integral is natural log of the absolute value, secant u plus tangent u. So if you remember the derivative of secant, it's close to, the integral of secant is very close to that. It's just the natural log of secant u plus tangent u. Not secant u times tangent u, right? The derivative of secant u times tangent u. Integral of secant u, natural log of the absolute value, secant u plus tangent u. Okay, plus c. Okay, so again, you can see some patterns in there and things, right? Especially, if you know all of your sine, tangents, secant, secant squared, secant, tangent, okay? If you know these, then you essentially know these as well. They're kind of like, opposite signs, and then just like their corresponding co-functions, okay, in a sense. All right? Cosine, sine, secant, tangent, cosecant, cotangent, tangent, cotangent, secant, cosecant, right? So you can that'll help you memorize and stuff like that too, seeing those co-functions and stuff. All right, but now we've got all of our trig functions. Okay, they're integrals, okay, for which we'll be responsible. So moving to number 5 here, letter A, we've got our problem, our integral that we want to find. Okay, remember this is cosecant of the quantity 3x squared. I'm going to put some parentheses in there to help us. All right, so what technique does it look like we maybe will need to use here? Probably use a U-substitution. Let U, okay, and what should we let U equal here? The 3x squared. It is inside the cosecant, so, as kind of like the tradition, right, we kind of use what's inside there. Okay. That 5 coefficient, I'm going to pull that 5 coefficient out front, so I'll make it 5x cosecant of 3x squared dx. Okay, we have an x dx right here. We don't have a 6x dx. I'm going to move the 6 over here, make it 1/6 du equals x dx. So now we have the x dx matched here. Okay, the x dx is matched, and so then 1/6 du will replace that, and so we'll have 5/6 integral cosecant of u du. Okay, and what is the integral of the cosecant? Well, we just did it, right? Negative natural log of cosecant u plus cotangent u plus c. So 5/6, negative 5/6, I guess I'll say. Okay. Natural log of the absolute value of cosecant u plus cotangent u plus c. And then we'll substitute in our u. So cosecant of 3x squared plus cotangent 3x squared plus c. Okay. It's not necessary to put parentheses around the 3x squared if you don't want to. Might not necessary, but I like to do it just because it shows that 3x squared is inside the cosecant there. I know it can be confusing about what's inside, what's outside of our trig functions.
Is there a math to find the derivative of the cosecant of u?
Like
The integral?
Like how? Like is there a technique for it? Yes, I'm sure there is.
Okay.
I'm sure there is, and I mean I would. It probably involves a little more trickeration than what we did with the tangent. But if you, you can kind of see, the starting point at least of it, because cosecant, I'm imagining where it's probably going to start is they'll start with rewriting that as like 1 over sine, and then we go from there. Have to again do some maybe trig identities and stuff like that to make it work. If you're really interested, I can look it up for you, and it's probably in the book, but I can show it to you if you're interested later. Okay? We should have time. Okay. All right, letter B. Integral of secant x times tangent x minus 2 secant x plus tangent 2x dx. Right. So, looking at letter B here, what might be a good strategy for us to employ? Break it up. Okay, and in fact, break it up. How do we know to break it up over what? The subtraction and the addition. Right. We can break this up into 3 separate integrals here. So integral of secant of x tangent of x dx minus, I'll pull the 2 out here too, integral of secant of x dx plus integral tangent of 2x dx. Okay, and Clayton, I still didn't ask, I didn't ask about the dx there and stuff like that. So I'll get to that though. I don't want to forget about that. Okay, I did not forget. I just didn't get to it yet. Okay. Mr. Wade, do I have to write the dx all 3 times? Yes. Okay, yes. You do need to write that dx for all 3 integrals there. All right, so secant x tangent x. What is the integral of secant x tangent x? Secant of x, right? Okay, well, yeah, I guess we do need to put the plus c in here. Might as well. Yes, good thinking. Good thinking. I like that. Horrible thinking, Lander. Horrible. All right, integral of secant. Yeah, so it'll be minus 2 natural log of the absolute value of secant of x plus tangent of x. Do I need to put another plus c? No, we can just consider it to be absorbed into the other constant there. So it's not necessary to put 2 plus c's. Okay. And then the integral of tangent 2x. Can we just integrate that as it's written? No. We have to use a U-substitution. So we'll let u equal what in this case? 2x, so du equals 2 dx. We don't have a 2 dx, we just have dx. We'll have to make it 1/2 du equals dx. Okay. Yes, you may. Clayton. Don't worry, this is all being recorded anyway, Clayton, so you can come back, and I can also answer questions too. So. Okay, so we're not quite ready to integrate this thing, so we have to rewrite it, right? It's going to be 1/2 integral tangent of u du. All right, so we're going to leave the integral symbol there because it's not yet integrated, right? After you've integrated something, you can drop the integral symbol. We haven't integrated that yet. So we have to rewrite all this other junk here. Okay, integral of tangent. This one we did, right? It is the negative, so it'll be negative 1/2 natural log of the absolute value of cosine of u. And again, we don't need to write the plus c. We already have a plus c in there. Okay, and so we finally get secant x plus c minus 2 natural log of the absolute value of secant x plus tangent x minus 1/2 natural log of the absolute value of the cosine of 2x. Oops, I'm off the screen. There we go. Okay. Question? We're good? Okay, I mean, please, yes, if I go too fast, yes.
You only need like one C for all of that?
Yes. Yep, only one C. So the idea is, right, we're doing 3 separate integrals, right? So it's technically, right, all 3 of those integrals should have a plus C on at the end of their answer. But because we're talking about some like random constant, we can kind of just combine all those random constants together. Even if like one C would end up being positive, one C might end up being negative, combining them all together, we can just say it's plus C, and they just kind of absorb all together like that. So it's not necessary. Yeah, not necessary. Yeah. Okay. Typically, the plus C is put on at the end there, but of course, since we integrated right here, the very first integral we did, we should put that plus C. Anytime you integrate anytime you integrate, the first integral that you do, even if there's 3 of them to do, the first one you do should have that plus C, okay? You don't want to save that plus C until the very end or anything like that. It's not something you tack on as like an afterthought. It needs to come as soon as you integrate, okay? It's not something you just like add on at the end because, oh yeah, plus C is an indefinite integral. It needs to happen as soon as you integrate. Okay, turn the page. So, what's my tie?
Yeah. Like, it looks like Buddha from here.
Well, it's kind of right.
I know.
Kind of right.
It's not Buddha.
No, but he's based off of it. It's Yoda from Empire Strikes Back.
Can't see it.
You can't see it?
2 Star Wars days in a row.
Did you see the movie yet? It came out yesterday, right?
It's coming out tonight.
Sorry, not really Star Wars.
Okay, I didn't mean to be snarky with that. I wasn't meaning to be like that way.
Are you watching it
I was trying to
tonight?
focus on getting the thing down. So yes, absolutely. 8 o'clock. Yes, sir. Mhm. Yes. I was, if you can believe this, okay, so I bought these tickets like a month or 2 ago. 2 months. No, it was 2 months ago. It was October. Yeah, right? So I bought them 2 months ago.
He's not here.
I was still too late for the first showing. Too late. Like the show had already been sold out. The first, like, I think there's a 6 o'clock and a 7 o'clock showing, and I was too late for those.
Nerds.
Yeah, 2 months early buying tickets. I was too late.
That's a good advantage of the situation.
I mean, yeah, that's true. It's true. There's like a quote from a show. It's like, I'm not a nerd. Nerds are smart. Anyway, so. Millhouse from The Simpsons. Anyway, so, all right. Integrals to which the log rule can be applied often appear in disguised form. For instance, if a rational function has a numerator of degree greater than or equal to that of the denominator, divide. Okay? So, evaluate the following integrals. All right? We can look here and see this exact situation, right? The rational function has a numerator of degree greater than or equal to that of the denominator. Okay, right? In fact, the degree at the top in this particular function is? What is the degree? 2. And the degree at the bottom is? 2. Right, so we are going to divide here, right? A U-substitution won't work. If we let u be x squared minus 1, the du will be 2x. We need it to be, something squared there. So we can do long division. Yes.
Algebra 2 all over again.
Algebra 2, pre-calculus, right? It's all coming together, folks. It's all coming together.
I
So-
Mr. Thompson's test on this. Yes.
Put your placeholder in, right? We have x squared We don't have an x, so I'm going to put a 0x and then plus 1. Is it necessary? Not really, but I think it's just helpful.
Well, failing this test is no doubt about that.
Okay. Long division, everyone's favorite. Okay. So, what times x squared gives us x squared? 1. 1 times x squared is x squared. 1 times 0x is a 0x. 1 times 1 is 1. Okay, and what do we do with this quantity? Subtract it. Okay, I'm not a big fan of like leaving that subtraction sign in front of the parentheses, so I like to change it to add the opposites, and I go through and make everything opposite. Okay, so x squared plus a negative x squared, that's gone, and it should be gone, right? That's the point of the long division there, is to cancel out that lead term. X plus a 0x is still going to be x, right? X plus 0, 1x plus 0, or negative 0, whatever you want to say there, is going to be x. And then 1 plus negative 1, 0, right? Okay, so we just have x left over here. Okay, I guess put an x plus 0 here. Okay, can we divide any further, right? Can I say something times x squared, that a nice number times x squared gives us x? No, okay, so what is this known as? The remainder, and we can put it over the x squared plus 1, okay? I think they're called the divisor. Okay, and that's the dividend, I want to say. So, right, because this thing x, right, hasn't yet been divided by that x squared plus 1. So we can say this is equal to the integral of what then? 1 plus x over x squared plus 1 dx. Too much. Mr. Wade, this is too much. Okay?
Are we able to just do U-Substitution, or do we have to do division?
So, I think first we should probably break this integral up, because we can integrate 1 without needing the U-substitution there. And so we'll make that separate. And then, yes, now, Mario, we will need to use a U-substitution.
I meant at the very beginning.
At the very beginning, a U-substitution would not have worked. Because, again, the point is, right, if we let u equal the denominator, okay, if it was x squared plus 1, then du would be 2x. And if you look up here, we need not just a 2x, we need an x squared plus, x plus 1 kind of thing. We wouldn't have enough. So, yeah, we need to do this, in other words. Need to. Okay? So we'll let u equal x squared plus 1, our denominator now. Du we equal 2x dx. Okay? Divide the 2 over, so we get 1/2 du equals x dx, because we just have an x dx there. Okay, so we can go ahead and integrate the 1. What is the integral of 1 with respect to x? It'll be x plus c. Good, we need that plus c in there. Plus the integral, we haven't integrated yet. I'm going to rewrite this, well, actually 1/2 the integral, I guess I'll say, of 1 over u du. Okay, because again, there's our x dx. That is that du right there, or 1/2 du, I'll say. So we get x plus c plus 1/2 natural log of the absolute value of u. And again, no plus c necessary there. So x plus 1/2 natural log of the absolute value of x squared plus 1. I'll put the plus c at the end. Not necessary, but there it is. Okay. If your integral is going to require some U-substitution, but some without U-substitution, you should really break it up. Okay, so again, here, right, we didn't need U-substitution to integrate the 1, so we're just going to break it up over the addition there so we can integrate the 1, and then we'll integrate this other integral using the U-substitution. Okay. So yes, Sean?
Wait, so why is this 1/2 positive and the other 1/2 negative?
Okay, so what is the integral of 1 over u? Natural log of u, absolute value of u, plus c, right? Okay, very good. What is the integral of tangent of u? Integral of tangent u, negative natural log of the cosine of u. So the negative comes from the fact that we're integrating tangent, not from the natural log part. The integral of tangent is negative natural log of cosine. Okay, that's where the negative showed up, why it showed up. All right, why don't you guys go ahead, try letter B. This is a definite integral here, but go ahead and try letter B. Okay, hint, the degree of the numerator is equal to or greater than the degree of the denominator, so you will need to long divide here, okay? So give this a try. I forgot how to do it.
I forgot to do long division.
Okay.
I didn't know how to do long division. I totally like went behind. That's why I realized that you can't just like.
Of course, if you want, you can use your calculators to check your work because it's a definite integral.
No way.
Way.
It is so lazy.
You program a calculator into his brain. Special contacts. Or just immediately gives him the answers. Wait, what's the integral? Are you done? Yes. What's the integral?
What is the one?
But it's from 6 times y. Yeah, but it's from 6 to 4. Looks good. So you get to.
Could have, if you wanted to, left and dividing 11 all in one. You want to also.
Like really nice. That's what you should have gotten. I did my long division right. Yeah. Well, we already knew that, but there's a new one to do.
Okay, yes. So you brought
actually kind of hurts.
Oh, yeah. Yeah, I agree.
4 minus 2 plus 4. 6 minus 2. If you do it one more time, I'm gonna stab you right in the chest with this dull pencil. Yeah. Think I won't? Drop that shit right in your chest. I'm a serial killer.
Me too, I still steal every morning. It's alright, Cody, you can joke around it, your life is quite fun.
Carter takes everything too seriously. That's why he does really good in school.
Carter, what's the answer?
Yeah, Carter. What's the answer? What's down? What's 12 minus 8?
6.
What?
I was trying to screw with you. It's 7, right?
I'm a child. Simple as that. I need to put in simple terms. Those are
There's ovaries.
I think
Take that.
there is an error.
I'm pretty sure I got this one.
It's definitely right.
It's definitely wrong.
So
You didn't even break it.
this is 7, but it's minus
There's one more.
I think I'm actually sorry.
minus the
I
quantity.
don't even.
I was thinking,
So it was 11.
I didn't solve for it completely.
11. 11. Make sure we're meter.
I'm gonna do that to Ryan Wojciechowski because he's going to the Star Wars movie definitely tonight. See him in the hallway. Carter, did you actually figure it out already? Can I see it?
Don't give it to him, he doesn't know how to do it.
I have an answer. I just don't know how to say
Would you look at that?
Before we were integrating this was you. Right? That's your wireless isolation.
I don't know.
How many people actually go?
What? To make this natural, absolutely.
We're gonna go on.
Or, and three, what you have, and then divide by 4 to 6.
So do you realize that I beat this level already, therefore I already know the answers.
Did you do the division in your head?
Oh, I see. Oh, I was like confused about that you're combined. Okay, I see.
Turn it out.
Alright.
So then make sure, no, so this is good, actually. That is the indefinite integral, but now you need to evaluate it from 4 to 6.
Wow.
So you got, so 6 in here, here, and
Yeah.
here, and then minus 4 in here, here, and here. Okay, that's right, yeah.
So then, like, we don't need to find the new,
So it depends on how you want to do it. There's two kind of ways to evaluate indefinite integral U-Substitution. Option 1, you drop the limit of integration and just do it as it's an indefinite
I was trying
integral.
to do two.
You're trying to do the second one? Okay, second one where you have it in front of you and you rewrite your limits of integration.
Yeah, because
So-
here I got the new
So when you integrate this, you want your limits to be from 4 to 6, because that's still another one.
These ones are still 4 to 6.
I got you. And so
But then
then,
these ones are the new ones, 4 to 2.
so then,
Carter, your answer's wrong.
the integral of
You got a plus
this,
C.
you haven't integrated this.
It's a definite integral.
Oh, natural, it must be 19.
Nothing.
Actually, it's right.
Because it's a negative 3 plus a positive plus 2.
I did have 19, but then I thought it was plus a minus 9. Okay. So then it's
So
a
we
minus
have-
minus
Great.
19.
You solved it out all the way.
And so now this, you want to evaluate, and I see your,
Well,
so you want to evaluate this.
got the same.
Am I the only one that woke up this morning and checked the FCDS to make sure school was closed? I woke up at 5:30, I was like, look, I need to go back to bed.
And then you want to evaluate
This
this.
was 6 points. So I didn't
Yeah.
think
We're at, we went back, that was our wrestling match. We go to, like, open up the doors.
Okay. Shh. Let's take a look here. All right, there it is. So let me run you through this because I know it's a little crazy. Okay, there's the long division that we knew we had to do. Okay, so first step here, make sure that you're adding and subtracting things correctly. Okay, it gets a little bit tricky when you're subtracting quantities, right? That minus sign distributes. That's why I like to change the minus to addition and then just make everything in here opposites. So we're just always adding terms here. You get 11y minus 3. Put an 11 here. You get negative 11y plus 22, and so you get 19 for your remainder. So this integral rewrites equivalently to this integral right here. Okay. I see here the 2y plus 11 is not going to require any additional work, so I broke it up, 2y plus 11 dy, integral from 4 to 6, and then plus, and I pulled that 19 as a coefficient in front of the integral here from 4 to 6 of 1 over the y minus 2. This piece was going to require U-Substitution, right? So we can break up just that piece. We can just break that piece off. Okay? So I went ahead and integrated 2y plus 11 to be y squared plus 11y, and that's going to be evaluated from 4 to 6. This, right here, I had to do a U-substitution. U equals y minus 2. So du is just dy. So this becomes the integral from 2 to 4 of 1 over u du. Notice I changed limits of integration here because we're in terms of u. It's not necessary to do that, right? You could just leave it the indefinite integral of 1 over u, integrate it, plug back in your y, and then evaluate from 4 to 6 if you wanted to. But I like using my u integration. Okay, so this evaluate from 6 to 4 was this right here. And then 19 integral 2 to 4 of 1 over u is 19 natural log of the absolute value of u from 2 to 4 evaluated. And so then there's the arithmetic, okay? So 102 minus 60, 42 is your limit, sorry, your integral value for this. And then 19 natural log 4 minus 19 natural log 2 is 19 natural log 2. Remember, we're subtracting here. Okay, so natural log of 4 minus the natural log of 2 is related to natural log of 4 divided by 2. And so it simplifies to just this. Okay, we can imagine factoring that 19 out, bless you. Factoring the 19 out, so you can do natural log 4 minus natural log 2, which is natural log of 2 then. Okay, and if you wanted to, you could also bring the 19 up as the exponent for 2, make it natural log of 2 to the 19. Alternatively. Question? Any questions? All right, last thing here, last little bit. Okay, a population of bacteria is changing at a rate of dp over dt equals 3,000 over 1 plus 0.25 t, where t is time in days. The initial population is 1,000. Find the population of bacteria after 3 days. So why don't you go ahead, take 30 seconds to a minute, set up the integral for this. Okay? This is we have an initial place. We want to find then the new population after 3 days. So set up an integral here. That involves some ideas with the net change and stuff like that. So hopefully your integral looks something like this.
Do you need that P of 3?
No, don't need to do that. Okay. But it would be correct in this situation. P is the function that describes the population, and then the rate of change of population is dp dt. So then P of 3 would be. Okay. All right. Question, Bryce. Absolutely, you can if you wanted to. Yes. Yep. So if you had 1,000 plus 3,000 times the integral, so if you had something that looks like that. Okay. Then that would be okay too. Okay. Now, this is not calculator necessary. Don't need to have a calculator here. I mean, obviously, if you want to get a precise value, you would need to do that. But I'm sorry, if you want to get like a single value, I guess I'll say you can do that. But really, it's not necessary, right? I mean, here's the integral, right? The U-substitution here would be the 1 plus 0.25t. Derivative of 1 plus 0.25t is 0.25 dt, which then means 4 du equals dt. And so we'll just do a U-substitution here. 12,000 then is our new coefficient, and our new limits of integration are from 1 to 1.75, and so we end up with 1,000 plus 12,000 times the natural log of 1.75.
Did you get the 1 to the 1.75 by plugging 3 and 0 into the U?
The U, exactly right. Yep. Sean? Okay, yep, yeah. 0 in here is 1 plus 0, so it's just going to be 1, and then 3 in here is 1 plus 0.25 times 3, so 1 3/4 or 1.7. Okie dokie. All right, so that's all I've got for you here. I'll get you guys started on your assignment. Okay, I'll put that right up here on Google Classroom.
Let's learn to call on the phone.